Hello, I'm going to talk about what Pyspark is. So, as you all probably know by now, we have a good bit of our privacy tooling built on Pyspark. And I wanted to make sure that everybody from sales to operations to even the engineers understand what Pyspark is at a fundamental level and why we choose to employ it. I think we can start by just imagining data, right? We process healthcare data, claims data. And so you can imagine data as represented by a computer in a spreadsheet format, right? And so you have columns and rows. You can imagine there might be columns associated with a patient ID, their height, their weight, and then the rows can be numerous, and each row represents a patient. We're all very familiar with this model. It's Excel files. Let's imagine, however, though, that we need to add a new column. And the column can just be the BMI of the patient, which represents the ratio between the height and the weight, right? If you were to write that formula into a spreadsheet and then drag it to the bottom, you might not even notice the computer processing it because who knows, maybe it's 1,000 patients. But let's say that data were to grow to 1 million records, 10 million records, a billion, 100 billion. Pretty soon, if you dragged that arrow key down to apply that formula across all 100 billion records, your computer's going to start to have issues. You see, the processing that's involved in that spreadsheet application is doing functions in memory, and at a certain point, it just becomes too much for the computer to handle. So if we were to move out from the spreadsheet application constraints, and we were just to write code directly on a device, it too would reach a limit at a certain point of scale. Okay, so enter into big data processing frameworks like Spark. And so quickly, let me actually just give a brief aside on why Spark exists in the first place. So the people at Google, when they were working on their search algorithm, developed something called MapReduce. And the reason they had to do this is because when they went to index the entire internet, there was a certain point in time where clicking the button to index the entire internet just broke all their machines and they couldn't do it. So they, just by virtue of their business model, had to come up with a way to get around this bottleneck. And what they did was they developed this algorithm called MapReduce, which is a fancy way of saying you have this very large problem. Can you break it down into a series of discrete small files that have like a shared state, right? And so instead of indexing the entire internet, can I index, Pokemon web pages in isolation? Can I index fitness videos in isolation, right? And then I stack them all together, and that's what MapReduce is. And a lot of large data processing systems operated on this paradigm, including Hadoop, which is the big famous one. However, Hadoop was slow, and in 2011, if I'm not mistaken, some researchers at Berkeley decided to come up with this alternative framework called Spark. And so Spark, the idea behind it is essentially just MapReduce, but in memory. And so what do I mean by in memory? So in computers, there's two different abstraction layers for storage. There's your on-disk storage, which is much more voluminous. That's your terabytes of disk space if you have it. And then there's something called memory, which is much, much more reserved and small. Usually it's 16 gigs, 8 gigs, 32 gigs if you're lucky. But it's much more faster, right? And so RAM is oftentimes attributed to memory. It just stands for random access memory. It's volatile. When you start your computer up for the first time, it's completely clean slate. However, on disk data, you can start and restart your computer all day long, keep it. So disk information is slower retrieval and access than RAM. Anyways, so Spark's big invention, which sounds pretty obvious now, is really doing that processing in memory rather than on disk. And so Hadoop would always try to load data, compute, and then write back to disk, and there's an overhead associated with that file input output. So after 2011, I think 2013 or so, something like that, after a few more years of research, it was moved to the Apache Software Foundation, and that's why it's called Apache Spark. Spark is built on Java primarily. We use Pyspark, which is the same core engine, but using Python interfaces. And so if you have, back to the original principle in mind here, if you have tens of billions of patient records and you want to do even more complex things than just calculating height and weight ratios, let's say you need to do an aggregation or count the number of equivalence classes against the dimensions of demographic information, such as gender, age, ethnicity. That's a very complex computational problem. So if you imagine tens of millions of records or billions, the computer can very intelligently, through this framework, this Spark framework, divide that problem up into a series of smaller problems that, once computed together, can reaggregate into the final answer. So that's kind of the full insight. Your machine that you're watching this on actually has multiple CPU cores. And so in my case, I have 16. What that means is I have 16 different processors, essentially, that can work on the problem. And so you might ask the question intelligently, what if I just have a really, really big server? Can I not just compute using all the threads available in that server and just get thousands of gigs of RAM? The answer is yes. That is called vertical scaling. So vertical scaling is when you get a very, very beefy instance. In that way, maybe you don't even need the Spark framework. Maybe you could just load 100% of it into memory, compute it across all those threads. However, even in that scenario, you have to deal with a lot of different problems. You have to deal with locks, which is sort of, can I compete for the same resources? Because ultimately, each of these different CPU threads, these processes, are going to be competing for the same resources to read and write the results to. And so there's a bit of, making sure that everybody stays in their lane. And it's expensive, right? So Spark is the framework for having a managed horizontal scaling layer, which means that multiple instances. And so I could actually have 4 different computers, each with 16 gigs of RAM. I would have a parent node and child nodes, and the parent is sort of the one that divvies out work to the children, who all in turn work on a subset of that computation. At the end, there's a reaggregation, right? And so it's not perfect. There are times where those child instances will go down, either due to network issues, maybe it's a spot instance and it gets revoked because somebody's willing to bid more for it. And so that's ultimately what Pyspark is. It's just a framework for thinking about distributed compute. The way that we write the code is as if it's just on a single machine. And then Spark is very smart and says, I'm going to take that problem, whether that's a query or an aggregation, which is ultimately a query, and farm it out among many instances. And so Databricks, what is its role in this? Well, Databricks is the managed compute layer that is running the Pyspark code. And so Databricks is very convenient because it will manage our Spark cluster for us. And so we can set a configuration that says we want anywhere between 2 and 10 workers, right? And we're going to operate on this data. So maybe for WebMD's data, it can run fine on 2 machines. And so the 2 machines that are running hot can take the problem. One can be the master, one could be the slave node, or the parent and the child node. And in another instance, maybe AbbVie's data is much more voluminous. Maybe Spark, and in this case Databricks, can look at the capacity of the machines that are running that problem and see that they're very, almost reaching capacity. Their CPUs are just spinning to the max, in which case they'll spin up more servers next to them and farm out more work to those new workers, right? And so that's Spark, that's distributed compute. That's why we have to do what we do. Ultimately, our goal is to run any sort of query or aggregation, a set of risk analyses in under 4 hours. You either do that, again, by vertically scaling or horizontally scaling. We choose to horizontally scale in most cases, spin up more workers, farm out that problem. And so that's Pyspark in a nutshell. Thanks.